Okay, thank you for inviting me here. And well, I'll speak about the relation which was kind of surprising for me. Maybe it's even obvious for specialists, but nevertheless, there is such a relation between arithmetics and integrable systems. And and I'm definitely not a specialist in arithmetics. The only thing my contact with arithmetics is just I teach it from time to time. But for integrable systems, I know them much better, in particular because I discussed a lot with Michel Audin, and I would like to devote my talk and my work in the subject to her memory. The plan is the following. So I'll give a definition. So the tau function, well, I don't know if how much you know what it is, but I'll give it my definition, which is kind of very different from the standard one, but it's such that you will see that it's kind of related to automorphic forms. And then the rest of the talk, I'll try to convince you that my tau function, the standard tau function, is the same thing, in particular that my tau function satisfies Kp, Toda, all this business. So, but the main tool, and my favorite toy for the last couple of years, is the Steinberg symbol. So the Steinberg symbol, maybe I'll just draw it here. Steinberg symbol. I just recall what it is. So this is if R is a ring, commutative ring, and A is an abelian group, which I'll both write, A will be written multiplicatively. So the symbol, which is denoted by curly braces, and they have, very remote relation to Poisson brackets. So this is, it's just coincidence, but it's standard notation. So the Steinberg symbol is a map from R invertible elements of R to R terrible, in fact, it sends the product of them to A, which satisfies the following axioms. So first of all, if you have two elements, B, C, it's multiplicative with respect to both arguments is kind of by multiplicative function. So this is equal to AB times AC. Then it's kind of antisymmetric. So AB times BA equals 1. And once again, I just write the group multiplicatively. So this is the only operation of the group. And then A B equals 0 equals 1 if A plus B equals 1 or A plus B equals 0. It's the only place where you use the ring structure of the ring. The rest is.
So the second condition follows. The second line follows if you use
this. This follows if R is a field, but if R is just a ring.
No. If the second ABBA equal 1 follows because if A minus A is 1, you can apply it and get the.
Right. Yeah. The second follows. Yeah. Well, they are not independent. Yeah. So this is a definition, and then I'll use actually. Much use just one particular symbol, particular case, and this will be the following. So if R will be the space of functions, the functions maps of S1, which is a circle, which I'll imagine as quotient R over Z, to C star, C. And so therefore R cross is just the maps, the same thing, R quotient Z to C star. And there is Beilinson formula, which gives that the symbol of two functions, so a Beilinson formula, symbol, that if you have two functions f and g, then the symbol is equal to the exponent of 1 over 2 pi I integral from x to x plus 1 log f d log g, and all that times g of x to the power minus degree of f. So what all that means, first of all, degree of f is just how many times f goes around 0, because this group, the group of non-invertible elements, is not connected. It's, well, and by degree I mean the number of times it goes around 0, so it can be written as a 1 over 2 pi I integral of d log f. It's just definition of the degree. It's not, well, if you see this formula for the first time, it's not quite obvious that it's well defined, but it is. So, for example, it doesn't depend on the choice of the branch of all logarithms. It doesn't depend on the choice of initial point x. And for that, well, because log f is not periodic function, so a priori, this integral, well, this integral depends on the choice of x. But if you multiply this correcting term, it is. And it can be interpreted also as a monodromy of certain connection on C star cross C star, but I will not go into details.
You need some small condition on the function to write d log g, like you need the bounded variation, some condition on the function to...
No, just no conditional functions, just periodic functions. Just periodic functions. Maybe smooth. They will be smooth. For yeah, let's assume that everything will be smooth. Yeah, except, well, I will need some generalizations for that a little bit later, but it will be yeah. Let's take them smooth. So, yeah, of course. So this is a symbol, and well, you can verify that it satisfies all these axioms. It's more or less obvious, except, well, almost everything is obvious. And it's also suppose we have, well, we can a little bit generalize this symbol and see that the symbol is a kind of multiplicative analog of residue. This integral is kind of multiplicative analog of residue. For example, if you have a function on Riemann surface, so sigma, it's Riemann surface.
Well, we can do just
like that.
The symbol is very C star, yeah?
The symbol, yeah, sorry, I forgot to mention that it is C star. Yeah, of course, and which will be my A. So sigma is Riemann surface. F and G are just functions. Well, functions with functions with and well with in isolated singularities. It's even not very necessary, but with well, just functions, yeah, with value. In C star, so if you have just meromorphic function, then it's a function which defined not on the whole surface, but on the whole surface.
So it's analytical without finite limit.
Outside finite many points, yeah. Yeah. And then it's just definition, and gamma is a path in the domain of definition, of course. Of f and g. Then, by definition, fg gamma is just the symbol of, I take the two functions and restrict them to gamma. And of course, this symbol doesn't depend on the homotopy class of gamma. So it's just like you compute the residue, then you take contour integral, but this contour integral, which is just a little bit more complicated than usual, but it's multiplicative. And also it's just notation. And another notation that if gamma is in P is a point in sigma, and F and G have isolated singularities in F and G in P, then just the definition FGP is just equal to the FG with respect to a small path around P. It's just notation. Small loop, yeah, small loop in the negative direction. And then you can compute the case that if F and G are meromorphic, then the Fg at the point P is equal to this is contrary to all that was definitions. Now it's kind of simple exercise that Fg equals -1 to the power degree of F degree of G, and this time degree is just the order of the pole, or 0, times P to the power F to the power degree of G divided by G to the power degree of F, and all that computed at the point P, because this ratio has degree 0, so therefore its function which has neither pole nor 0, so you can restrict it to this point and compute this value. And well, I'll mainly speak about functions, homomorphic functions and all that, but this formula can be generalized for a ring, for example, of rational numbers. And you can define a symbol. There's a remark, number theory remark that Fg, the same formula, Fg is equal to the same thing -1. This is just literally the same formula, but with P prime, F and G in Q, and P prime gives a symbol of Q, it's of Q. So you do, the only difference that now instead of computing at the point P, you compute mod P. So this belongs to Z over PZ cross. So it's kind of analog between meromorphic functions and just rational numbers. And of course, also, if you wish, you can extend this symbol to QP, because well, the degree is a function which is continuous in QP, so you can continue to extend it to QP. So this is the symbol. Now I will define something which I'll call tau functions. So definition, I have maybe I should just mention that well they started to play with symbol. I was teaching at the same time complex analysis. And I realized that this is very useful just to teaching complex analysis. For example, if you want to do the following, you compute the symbol of 1 minus z over a over z, sorry. It's just, I'll give an exercise. So 1 minus z over a sine of z and you take for gamma a path which is just a large, this is gamma, this is a large rectangle, which doesn't pass through zeros of sign. That you can prove that it tends to 1, and on the other hand, it gives you, well, you can compute the symbol, and how you compute the symbol. You take, well, you restrict, as usual residue story, so you restrict to the integral over log path to integrals around zeros and poles of your functions, so which are somewhere here. And this will be 1 over sine of a times product of 1 minus z over pi n. Yes. And this, the fact that this is equal to 1 gives you a product formula for sine. So it's kind of easier way to prove the product formula for sine than the standard one. This is just a remark about usefulness of a symbol, even for elementary mathematics. Now I go to tau function.
Right. So it goes, limit is 1 as what? As a goes to...
As the path goes to infinity. The path goes to infinity, it becomes large.
Ah, okay.
Yeah. So here is finite product for one particular path.
But the product is with z, and then sine is of a.
And fine.
A, of course.
Yeah. Z disappears completely.
That disappears completely. Yeah. Sorry. Thank you for this remark. Yeah. So here it is just one of the applications, but well, there are plenty of others. But one of the what I'm going to do, I now have everything to define my tau function. So what is tau function? Suppose you have sigma Riemann surface, as before. And P1, etc., PS just points in sigma. And I take tau, which takes a collection of local functions in this point. So f, well, for some reason I would take f1, f s minus, for I'll explain what it is, to c, where fi minus is a function, local function, local function of the form fi of zp, zpi, zi. Zi is local coordinates. Zi is local coordinates. Local coordinates around pi. And here is equal to z to the k I z to the k e to the t1 t minus 1 z to the minus 1 zp to the minus 1 plus t minus 2 z to the minus 2, etc. This is a finite polynomial.
And keys could be positive integer.
But zi, sorry.
No, z, and also get zi to power of
Minus 1, minus 2, etc.
Before the exponent.
This is k in integer, positive or negative.
And that's also zi, right?
There was zi, yeah. So the function of this type. This function is, well, the functions of this type, yeah, well, strictly speaking, I would do the following. So this function belongs to the space of functions what is quasi-meromorphic. So the function such that the logarithmic derivative is meromorphic. So this belongs to meromorphic, quasi-meromorphic, quotiented by meromorphic, quotiented by holomorphic, sorry, holomorphic non-zero. So this is kind of more invariant way to define what kind of functions are there. Maybe before going to that, I will just explain that what this function plays certain role. They kind of remark.
But holomorphic is always non-zero is always quasi-meromorphic.
Yes, you don't need.
So you don't need you can just say, and then you need to modify the formula by multiplying by something, some factor. Like you can multiply this by a constant or by something which doesn't vanish.
Yeah, but I want to just really quotient by functions. No.
It's quasi-morphic. It's quotient space.
It's quotient space, sorry. It's quotient space. So you take quasi-meromorphic function modulo multiplication by something holomorphic non-zero. I need to be non-zero because otherwise this k is not well defined.
Yeah. Okay. It's a quotient.
It's quotient by yeah. If I erase this quasi, this quotient is just z. And if I add quasi, then I get one integer and many complex numbers. And the remark is the following, that if you take this quasi-meromorphic function f, and then you take the f quasi-meromorphic, well, f of this belonging to this space, then the quotient f g and g holomorphic non-zero, then this is a character. If you fix f, then you can consider it as a character of holomorphic non-zero. It's just a way to write down a character of holomorphic non-zero. And my big problem with periodic numbers is that it's kind of not possible to write down similar formula for in this number theoretic context. But because there are no functions, no periodic numbers which can be written as 1 over minus 1 over p. So this doesn't exist. But if they were, so characters of rational number could be written as a symbol. Okay, so now I come back to tau functions, and tau functions by definition is a function which has this property, and it has the following. So it's such that, well, I just this function such that for any quasi-meromorphic function on sigma, well, with poles at given points with singularities.
So it's invertible, let's say, or maybe you add new poles or new singularities.
Well, for simplicity, I imagine that I don't have new poles. All poles are old one. But well, it doesn't matter because you may imagine you can always add some ones here as you can imagine that you have infinitesimally function. You have function at every point of the curve, but it's always one except finitely many places. With singularity, well, it's in the bracket with singularities. In P1, etc. PS. I have just the tau of F1 minus Fs minus equals to the symbol of G plus f product over alpha, g minus plus alpha, f alpha minus, or it's not necessary to actually write g plus, g alpha, f alpha, f of tau of g alpha g1 minus f1 minus g minus g s minus f s minus. So what it means? It's just kind of central formula for the story. So I take some functions for any meromorphic function g. So you take global function g, which is defined everywhere, and then you do the following. You can take this function, you can restrict to the vicinity of the point p alphas. So if you have you take the point g alpha, you restrict to the you can present it as a product of g alpha plus and g alpha minus. It's not canonical, but g minus is actually canonical because it's an element of the quotient. And g plus is not canonical, but g minus is canonical, g plus is not. But the symbol between here, well, yeah, g plus is not. But you can, well, the symbol actually doesn't depend on g plus because it doesn't depend on how you choose g plus. Because the symbol between minuses, if you have two homomorphic functions, then the symbol between them is equal to 1. And if you have two functions with minuses, they are also the symbol is equal to plus minus 1, actually. Well, there is some sign here you need to write, and I don't want to speak about this sign because it will take some much time.
No, I really didn't get. G minus is an element of quotient well defined, so this
yes.
The right answer.
Here you do define.
Yeah, but the middle term is not really.
Middle, you mean this one. You take a symbol between g alpha. Well, strictly speaking, g alpha. There is no plus or minus here. Yeah, it doesn't matter. So this is the. Well, you can actually write plus here, but the answer is that it doesn't depend actually on the choice, because if you have g, the minus part with this minus part could give 0, so it doesn't depend kind of choice of minus. But tau function depends on the local coordinates at the point, so this is anyway.
Okay, because otherwise
it's not. And that symbol is at each point p alpha, or so which?
It's product of alpha. So you compute at every point. You have a surface. Sorry, you have a surface. You have points, and at each point you have your own function f. Here you have f1 minus. Here you have fs minus, etc. And then you take just global function. Take the symbol at each point. You have two functions, f and g. You compute the symbol and take product of them. At the point p alpha. Yeah. Thank you very much. Of course, it should be written like that.
Absolutely. Doing the sentence lesson 96, it's tau functions vanish if you line bundle which you use as f as sections, something like this. No, because you consider this f minuses, yeah?
Yeah.
It gives you a way to glue
line bundle, right? Right. Yeah, and well, you can see that it's a function on the space of line bundles. Actually, it's a section of a line bundle on Jacobian, because it's a trivial. If you have trivial line bundle, it's vanishes. Well, it's equal to 1. Yeah, exactly. So that's what Maxim said. That essentially this is a function which you have this space of f's, so collection of f alphas. And you have an action of the group which with elements which is g, and the quotient of this space of f alphas by G. This is just Jacobian of my curve. And tau functions are in bijection with section of line bundle on the Jacobian. And therefore, well, in particular, Jacobian is compact, so everything is unique. Well, the function is not unique, it's just finite dimensional, but you can choose, verify that this is actually unique, up to multiple.
It's the same called Heisenberg functions?
No, a Heisenberg is more or less the same thing, but if you add, if you have here z at some extra point, so you have what z means that is a particular case of such functions. This is so this is a well now here once again I'm not just specialist in number theory, but this formula is kind of well, as far as I learned during the last couple of months, and I read books about automorphic forms. So this is a well, all these are just characters of the ring of well, this symbol is a character of the group of meromorphic, quasi-meromorphic function of my surface. In particular, meromorphic, if you wish. If you take this G can be meromorphic, and that you get a list of character, and so this, if you multiply the arguments by this element, the function is multiplied by the corresponding character. So, well, it's GL1 automorphic form, as far as I understand what it is. It means. Well, now the remaining time, I will try to convince you that the definition I gave you coincides with the standard one, and in particular that this function satisfies Kp, for example. So why tau is standard? Pardon?
Tau is tau.
Why is tau is tau? Exactly. So this is standard. The idea is the following. So let's consider first of all another role of the symbol, actually equivalent to this one, but less. Let's consider this. The group B is a group of functions on a circle. Just so I defined already that group of functions on C1 to C star. And let's consider B plus and B minus. Well, the subgroups, the following. So if you have a Riemann surface, you have any path on this Riemann surface, then B plus are the function on the circle which can be extended homomorphically to the left, and B plus is the Riemann surface which can be homomorphically prolonged to the right with some additional condition of behavior at this point. For example, here you allow a pole at one point and the residue with residue 1. So this is, here you have B plus, you have B minus. For example, if you have a Riemann sphere, then you come back to the function the composition of any function of G plus and G minus as it was before. So any function can be decomposed into, well, positive powers and negative powers. Then I claim that there is I can define the B hat as a central extension of B. And it's given by the following formula. So if you have, elements of elements of this central extension can be written as X F hat, where X belongs to C star and F belongs to to B. And the product is defined that x f times y g is equal to the g minus f plus xy fg hat. It's just a definition of the product in the central extension. So you have a central extension of your algebra. On the other hand, you can do the same story. You have the same surface. You have S1, so let's psi L, sorry, the space of 1/2 differentials on S1 on the same space. And also there are L equals L plus plus S minus, L minus. For example, that by the same principle, this is extendable. So this is extendable to 1/2 differentials, extendable 2/2 of sigma. And you can define the following algebra, which I'll call f hat. This is equal to the Clifford algebra of f plus, well, I can f star, or the dual to the 1/2 differential is still a 1/2 differential. So it's not necessary to distinguish between them, but I will do. So let's take the sum of f and f star.
F is L?
Well, sorry, L. Thank you. You have L plus L star. And this is a Clifford algebra. L plus and L minus, etc. So this is well, I already have L plus and minus. So this is this Clifford algebra, and I claim that there are two maps. One map which takes B hat to f hat. Maybe I write this way. And there is it's called boson-fermion correspondence. You can take B to F, and also you can take, it's not F0, well, maybe, to F hat, and F to B. Yeah. So there are two maps. And what is the map? This map is just what is B0 is just the subgroup of B of function of degree 0. So this is degree 0. And this map is given by the following. So you take the function f and you send it to x to the integral of epsilon comma wedge epsilon star d log f. So log f well defined because the degree is 0, and epsilon, well, it's a just skew-symmetric form, which is not d, no d. Epsilon times epsilon star is already one differential. So you multiply it by a function, and you get, and this is skew-symmetric form on the space of L plus L star, and exponential. It's just, this map is just a spinor representation, because multiplication by fx, well, bx on L by orthogonal transformations. You multiply, you have an action, f sends epsilon epsilon star to f epsilon f minus 1 epsilon star. this is orthogonal transformation. So if you have orthogonal transformation, you can write down as an element of the Clifford algebra by standard speed representation.
But here things are infinite dimensional, so you have to be, here everything is infinite dimensional.
Yeah.
So you have to know what you mean by this. It's formal.
Yeah, well, of course. Here it works. The problem is really, well, there is some problem where degree is not 1. No, not 0. There we have problems, but, well, I'm not going to. I'm just going to represent B0. I don't need anymore. But this is kind of on a level of Lie algebra. It's very easy to verify that everything is fine. Everything is finite, actually. And then you just generalize to, well, take the exponential. But it kind of works. And well, I also wanted to explain how to go other way around. And there is a formula which is essentially vertex operator, but in terms of symbol is kind of easier to write. Namely, let's consider the function psi a. Well, let's a in the circle, and psi a is equal to the limit. Then a goes to a plus, a minus goes to a of z minus. I imagine now the circle is sitting in the complex plane, so this is just unit circle. Z minus a minus, z minus a plus, where you have a minus, here we have a plus, 2 points, and they tend to a point A on the circle. So for before taking limits, it's just a good function. After taking limits, not a good function. This function is have the following form. So its logarithm is equal to 0 until a certain moment, then it jumps to 2 pi, then it continues. So this is the logarithm of my psi I. So it's a function which makes one loop. It can be interpreted, as far as I understand, as well. Tau function belongs to Sato, and this belongs to also an object invented by Sato, which is called hyperfunction. But so this is a ratio of two functions which are not well defined on the circle. But this is yeah. And the easy verification shows that if you compute psi a, psi b plus psi b, psi a with hats, of course, this is equal to 0, and and I have also the same thing. I can do psi. Sorry, I just don't want to start another blackboard. Psi a star is just psi a inverse. Very, very simple expression. So you take just an inverse, and psi a inverse, psi b, well, you can write plus psi b psi a inverse equal to 2 pi I delta of a minus b. So this is a really fermionic algebra, and it gives you a map by this very simple formula. Well, of course, in the limit, you need this time. It's really you need to take care of the limit, but correctly. But there is the map other way around. And well, I have no time, but I want to say that if you take just this formula,
Is it the delta Dirac delta as a distribution or as a?
It's a distribution, yeah. And the idea is that if you take this expression, you multiply by test function, you integrate, and then you use this formula of, I don't know, Cauchy formula, and you get this fact. In the limit, of course.
Which measure?
Well, this formula is just a standard measure of S1 in order to verify. But of course, it's A is half. It's the expression if you take any curve, then A is actually half differential with respect to A, and you need to multiply to test function, which is also half differential, and so all this stuff. Yeah. But what I want to say that tau, what is tau of well, this definition is just tau of f1 minus etc. fs minus is the following thing. It's just you take the product of this. Well, let's take here, I don't know how it's called, A. A is a map from bosons to fermions. So you take the B of A of F1, A of Fs, and this expression will be the expression in terms of Clifford algebra. And this expression is in terms of Clifford algebra, and this one, this brackets is a map from Clifford algebra from F to C, which is by definition is something that if you have well, xv is 0 if v in L plus, well then, well, you can verify that this expression satisfies this relation. Well, my main relation, which is hidden somewhere, this one. So this expression, if you write it in fermionic terms, then you can verify that this satisfies this relation. It's just one line proof. Yeah, but this expression is just a standard expression for tau function. It's very easy to verify that it satisfies Kp, etc. So I have no time to write it, but it's really five lines. Sorry for that. I stop here. Yeah.
Questions? A plus B equal 1 plays no role.
Plays no role. Here it plays no role, yeah. Yeah. But, well, it will place because this tau function, for example, if you have tau function with all coordinates non-ramified, so all t's are equal to 1. So you have function of integers, and these are actually cluster coordinates. And then, well, then it plays a role.
Is it possible to relate to some kind of cross ratio, generalized cross ratio?
Well, cross ratio is kind of particular case of that, the other way around. It's for example, I don't know, cluster coordinates on flags are just particular case of this tau functions that you have. Well, you have, for example, if you consider all t is equal to 0, then you have a discrete function of discrete variables which satisfy octahedric recursion and all that. So it's also something which tells that octahedric recursion is just natural in have the same status as Kp, for example.
Is it written?
Almost. I promised to write it by the end of this week, but
Other questions?
In this special function you described this is what you call subtype functions. Is it possible to understand in terms of Polishuk-Kazhdan?
I don't know. But no,
maybe it's a way to.
It's a hyper function. Well, yeah, this is kind of, yeah. Well, this is in our point of view on generating generalized function. This is more convenient to this.
Okay, then.
Thanks.
Ready?